Okay, so one of the things that we want to do is we want to show the infinite uncountability of the Cantor set. But in order to do that, we're going to need to build up some basic definitions, most of which the previous group has already covered, but we'll just go through them briefly. So cardinality, the cardinality of a set is the measure of the number of elements in a given set. Two sets have the same cardinality if there exists a bijection from set A to set B. Next slide. A set S is countable if it has the same cardinality as some subset of the naturals. An alternate definition would be a set S is countable if there exists an injective function from S to the naturals. Next slide. A set is countably infinite if there exists a bijective function from S to the naturals. Next slide. Not all infinite sets are countably infinite, though. As we saw in the last class, the previous group proved that the reals are not countable by showing that there does not exist a bijection from the naturals to the reals, which is similar to what we'll do in order to prove that the Cantor set is not countable. So like I said, many sets are uncountable, including the Cantor set on the closed interval 0, 1, which we will eventually show. So in order to do this, I want you guys to keep in mind we'll show that there does not exist a bijection from the naturals to the Cantor set. Okay, so consider this Cantor set. We can denote each level of the Cantor set as C sub 0, C sub 1, C sub 2, and C sub n, all the way to C sub n. So this is C sub 0, C sub 1, C sub 2, and so on. Okay, so we want to be able to talk about each interval specifically, so we let I sub nj represent that where n and j are in the naturals or 0, and n represents the level of the Cantor set that we're talking about. So I sub 2 would be 1, or 0, 1, and 2, and then j represents the specific interval on that level. So, for instance, z is in the interval 2, 3. Z would be in level 0, 1, 2, and would be in interval 1, 2, 3. Yeah, next slide. So we want to show an element of the Cantor set is analogous to a path along a tree diagram, because that's going to help us with our proof later on. So we want to do this, next slide, by considering the interval, the closed interval 0, 1, continue with the deleted middle third method that we've been doing, and the interval to the left of the deleted third represents a movement left on a tree diagram, and the interval to the right of the deleted middle third represents movement to the right on a tree diagram. So for all x in the Cantor set, and for all I and n, we've shown that x is in Cn. Thus, its location in each piece is described by a path in the tree. So if you give me an element of the Cantor set, I can show you that there's a path in this tree diagram. Next. In order to show that this analogy is sound, we need to prove three things. One, a given x in the Cantor set has only one path. If x and y are not equal, then x and y have different paths. And for all p in P, there exists a C in the Cantor set such that f of C equals P. And P here, capital P, are paths. But this is essentially saying that we want to show 1, well-definedness, 2, 1-to-1, and 3, onto for some function. Okay, so I'm going to show well-definedness. So we want to show there exists a function in the Cantor set to the set of all paths in the tree, such that for all x and c, f of x is well-defined. So let x be in the Cantor set. Suppose P1 and P2 are both paths describing x's location. Next slide. Suppose by way of contradiction that P1 does not equal P2. Then there exists an n and n such that first time on level n, P1 does not equal P2. Essentially saying that if we're starting at the top of our tree diagram, two paths are moving identical in an identical fashion, but at some point must break apart. because the paths are not equal. So basically what you're saying is that this x lives in two different segments of path. But we know that that's a contradiction because these intervals of paths, which we're using to be interchangeable at this point, are disjoint. So that can't be true. So we've shown that for all x and c, f of c is well defined because a given x and c has only one path.